Last time we talked about some kind of hypothesis function, and in this hypothesis function we came to know that some function, you can say this can be expressed in a linear equation, and this linear equation, once we are talking about linear equation, this gives us a concept of a line. And we studied various parameters and importance of these weight parameters, and we concluded that linear regression help out to predict the values for continuous data. But at the same time, this hypothesis function is used for a classification purpose. And once we are talking about the classification, then of course we are expecting some kind of binary output. And the binary output, you can say 0 or 1. 0, once you can say that the system, or you can say features are not up to the required standard, are not meeting the expected values, and once there is a one value when features are expected to the required output, or you can say in case if I give you some kind of an example, these are, you can say, some size of the tumors, very small in a brain. Clinical expert decides, yes, these are not a big issue for brain tumor, or you can say cancer, but the size, okay, are some kind of a negligible at the 0 position. But once the size is a bigger one, then suppose this one in a graphical notion at the position of 1, then clinical experts say if the size, okay, this is some kind of size, okay, bigger size, not of the 0 size, some kind of a point value. So the clinical expert will think that if the size of a tumor is bigger than the 0, okay, here this means that somewhere here near to this 0, small negligible value, but once the size of a tumor is bigger, then clinical expert, neurological expert will say, then definitely it's a tumor, or you can say it's malignant. Malignant means very dangerous. Malignant tumor, and this one is, you can say, benign. Yeah, very small or negligible things. And this can be predicted with the help of some hypothesis line. You can say, and this hypothesis line is kind of this one. But sometimes if we are talking about some mid value, or okay, this one is some, okay, this point, you can say 0.5. This is the central value. This kind of a mid value threshold decide the upper than 0.5 size of the tumor will be considered as a malignant one, dangerous one for the patients. If less than 0.5, anything can be acceptable. But this line create trouble once you will have a sir, मैं पहुंच गया हूँ. Thank you so much. जज़ाकल्लाह. वालेकुम अस्सलाम. जज़ाकल्लाह. Thank you so much. मैं पहुंच गया हूँ, क्लास में हूँ. Thank you so much. I'm so sorry. I informed Dr. Arif, but just saw the message. Okay, so in this case, what will happen? This line, these few tumors, okay, are beneath. These are you can beneath the line, this hypothesis line, and can be categorized as a benign. Though these are not a benign one. Are you getting my point?
Yes.
So our decision, this line, or you can say this line is kind of a decision boundary, is now creating problem for us. So with simple, you can say linear, with simple line. Once I am talking about linear mean line, then this creates trouble for us. Or you can say this follows some kind of a step function. Step function, and in step function, your lights, okay, these lights, for example, always in an off position, you can say it's at the 0. But once I turn on these buttons, the step function, it will turn on and say it's 1, and remain it's in this state. This is the step function. But this step function could not help us. This is a binary operation, just 0 and 1. But sometimes it's also possible that the size of a tumor can be somewhere here, the 0.65, 0.7, then this is a problem. Linear, okay, regression could not help us, or could not devise a good suggestion. So in this situation, we are using the logistic regression. This logistic regression is also known as sigmoid function. And the concept of this sigmoid function is really beautiful to help us that is somehow, you can say, this hypothesis function lying in between 0 and 1. Okay, just make it more simple. Okay, so such that we will say that this hypothesis function basically equivalent to the function of g, such that g is, okay, this g is technically representing sigmoid function. If there is no g, then of course this hypothesis is kind of a linear thing, linear regression. Okay, you can say theta naught plus theta 1 whatsoever extension. But if we are using this, we are considering another function into function. Some of you may be familiar, okay, composite function. So here we are using the first function on the linear, okay. So once and suppose we are considering this one equivalent to some notion or alphabet, kind of a variable z, then for simplification purposes we can say this, and this function, this sigmoid function, technically equivalent to the g of z. You know what is the meaning of z? Z means theta, okay, hypothesis function inside, okay. So I, instead of the, so we can write 1 over 1 plus e minus z. This is a very beautiful concept in itself, and so in this concept there is a, okay, suppose a line, this is a 0, this is a 1, this is the 0.5, and sigmoid function is, you can notice this is not a straight line. This is kind of a, okay, adjustable, you can say, this line. So here you can say somewhere is peak, but some kind of a, you can adjust it according to your desired output. And here this z, okay, you know this z equivalent to this one. We can consider various formation of this. Let me explain it one by one. And of course, there are X features, and corresponding to these X features, the number of examples, you are getting the possible output. Okay? So, in this situation, you can interpret the hypothesis function such that if we have some x is kind of a data features with some x naught or x1, there are two features. In case suppose the tumor, talking about the tumor. I don't know exact spelling. I think you. So you can say like similar. We are talking about the house. What we use for the house, x naught should be equivalent to what?
1.
1. Brilliant. So, and you can say x1 kind of a size of a tumor. Size of tumor. So this is some kind of a vector, in bold or whatsoever. So in this, you can say if your hypothesis function, or you can say g of z greater than or equivalent to some kind of a 0.5, then the tumor is kind of a malignant. And if this g of z less than 0. This one equivalent to that at the boundary best possible fit, exact at the boundary or greater than 0.5. The another option left to us, only less than 0.5, maybe 0.4999 whatsoever. Less than best fit, then it's the benign, not very much harmful. So in this situation, we need to check out this different decision boundaries. Very much important. Decision boundaries, suppose we are talking about the same thing, some kind of a tumor size, and we can consider in the previous case, we know we are talking about the tumor, x1, just consider it's one thing. Another here, like I'm following this vector, this vector. I'm talking about, no, this is the tumor, so I'm this one, so x naught somewhere here, and x1 is the one vector, suppose x2 is the other vector, and I am considering here the decision boundary between the malignant and the benign. For example, suppose these are the malignant. This being an expert, I can say this one. These are the red ones, cross some kind of malignant, and these are the benign. So I want to separate them with the help of some kind of a decision boundary. The question is how we can do it. Of course, we need to consider some kind of a hypothesis function. And this hypothesis function, according to our knowledge, can be composed of various weight parameters, theta naught plus theta 1, x1 plus theta 2, x2, or some kind of a, so you can consider the weight parameter here. And the weight parameter, as I told you, the one very important thing, this one is the biased, intercept value. Suppose it can be anything, it can be anything, or you can say very less chances for a normal human to, have a tumor cells. So you can say -1, and suppose this one, theta 1 is just kind of a normal way, 1, and theta 2 is also 1. So the vector, okay, so in this situation, weight vector minus 3, 1, 1. This is the weight parameter. Is come by following the intercept. Technically, we will evaluate what's the weight. But here, just I'm going to explain the decision boundary, and so we can imagine that we are familiar with the weight values. Okay, with the help of an equation of normal, you need to know what's the weight value. You need to predict the weight value. But here, for our general understanding about the decision boundary, I said that we observe the weight value kind of these. So, in this situation, if you are going to consider some kind of a, okay, hypothesis function such that you said this one, and of course you need to multiply this with what? You need to multiply theta with x, and in this case you are this theta, okay, this one minus 3, 1, 1 a moment ago I come, and x, you know, here x naught, okay, forget about this, okay, just you can say mention 1. X naught is the bench value for tumor, x1, x2, or you can say greater than 0, okay, by this hypothesis. So by value here you can say x1 plus x2. So now there are 3 possible choices. Remember, okay, this is the beautiful concept, please try to understand, stay connected. There are 3 possible choices. First one is minus 3 plus x1 plus x2 greater than 0, minus 3 plus x1 plus x2 equivalent to 0. The last one you can understand, okay, if I do not consider this one, I consider this. So minus 3 plus x1 plus x2 less than 0. Are you getting my point?
Yes, sir.
Is there any query? No? Very simple. Now, first of all, I would like to understand this one, the central one, this one. It is telling us some kind of a best fit, exactly equivalent to. So, how? Minus 3 plus x1 plus x2 equivalent to 0. We can express this x1 plus x2 equivalent to 3. And this is what? Equation of line. No square value, okay? No quadratic. So, my children, this is very simple and very beautiful. You can notice if we have 1, 2, 3 and 1, 2, 3. If in the equations x1 plus x2 equivalent to 3, if I considered, if I am talking about this one, x1, and of course what I need to consider, x2 equivalent to 0, okay, because I am talking about this one, this, okay, there no height, no height, okay, suppose it's the y, okay, I did not use the y because we are usually using the y for prediction, kind of some estimator, so x2 is the vertical curve, so no height. So this is the 0. In this situation, your x1 is what? Equivalent to 3. So here 1, 2, 3. So this is the point. Are you getting my point? So again, once there is no change along x1, you are talking about the x2 only, then x1 will what? x1 will 0. So you are considering x1 0, then you will get x2. x2 is what?
3.
3. So 1, 2, 3. My children, it's very simple. We need to connect, okay? Don't worry, this is just, so it's a kind of straight line. What is this? It is presenting some kind of best fit. Okay, now we need to notice if the case once in this situation greater than 0, okay, or you can say x1 plus x2 greater than 3. This will tell this one, x1 plus x2 greater than 3, that 4, maybe 5, are you getting my point? Malignant. So if you are talking about x1 plus x2 less than 3, then you are talking about this area. Benign. This is a decision boundary in case of a line, okay? So the things are simple. I am really sorry if I am not explaining it in a very well way, but let me explain one more example for your kind attention. For example, the five, because this value is 1, okay, usually theta 1 and 5, what will the answer? Actually, there are too many points. 1, 2, 3, 4, 5. So this shows that this side y equal to 0 and this shows y equal to 1. Binary. Always you will get binary, okay? There is a classification in the two possible choices. I will also explain the multiple choices, 3 choices, 4 choices, 5 choices, okay? But in this case, you will get this. So of course, this is the blue one is the best fit. And of course, if you are talking about x1 greater than 5, then you are talking about this area. And if you are talking about less than 5, you are talking about this area. Is it clear? Very simple, okay? Let me explain one more complex example so that you will get it. For example, yes please. Yes please.
Thank you, sir.
Yes please. X. Okay. In this situation, we can say x is the size, or you can say if we are talking about a size, it's kind of a one unit length, or x square mean the area. Okay, you can say if this is the this size representing only length, this can be somehow length into width, or you can say scale area. Okay, size x, and this is x length into width gives some kind of a so variable is the same but power is changing. In this way we are getting the polynomial sense, polynomial set of equations, and which can be further categorized with some, if we are supposing some weight parameter. For example, we are talking about the blood inside of our brain, or we want to recognize the tumor, which is of course the intensity level of blood, or you can say the amount of blood in form of a clot. Suppose the vector is encompassed of the various weight parameters, weight values. The first one is the -1. -1 is showing that if usually we do not consider the blood in terms of a tumor, if it is flowing in a very thin, or you can say that some kind of a so chances are very minimal. So we are considering it's a -1, or once there is no clot, no tumor. So if we are talking about the red blood cells, of course the weightage of this is also not very much. -1 is representing once the very thin, you can say, intensity of a blood, and here we are giving some kind of a normal normal intensity of the red blood cells with 0, normal intensity of the white blood cells also 0, but if the intensity of, you can say, clot of the blood cells, red blood cells are making some kind of bigger molecules, then we can say it's 1. If we are noticing the intensity of a white blood cells with a higher amount of volume, we are again saying it's 1. So these are basically the weight value. Weight value once we are just ignoring, okay, very much ignoring, minimal, that is kind of a very thin. So of course it cannot be a tumor, and this is the normal 0, this is the normal 0, this is a little bit higher in its size or volume, you can say. In the clot, blood clot, we say higher weight, this is a little higher. It can be 1 or it can be 3 or 4, whatsoever, it depends upon the situation or the depend upon the certain parameters. For example, if some patient in the older age, you can say you can give its weight more than the child, so the flow of blood, as you can say, of course, in old age is not very much in healthier position. So these are the weight parameters we are encompassing in one vector. Another vector, we can say the hypothesis with these values can be noticed. If we are talking about the blood cells or the tumor inside our brain, then the first one is the size of the normal blood, and okay, this is the red blood cells. This one is the ones you can say the white blood cells. Wait for the white blood cells, and once you are talking about the little bit intense, these are the X1. Basically, X2 are the features, okay, of the red blood cells, white blood cells, and this one is the you can say weight. Once the volume or intensity of the red blood cell is high in form of clot, you can say in the scale form. Okay, a moment ago I explained what is the scale. Okay, so volume, some kind of a huge simple length. So this one are the scale. Similarly, you can consider cube. So become polynomial. So if we are talking about the white blood cells, we can also say like this in the scale form. So here we can notice this one X1 red blood cells. Here is also red blood cells, but in form of a scale. This one is the another one. You can say white blood cells without scale, and here with scale. Basically, again white blood cell, but it's the volume of that white blood cell, and you can say in scale form, the area is higher than the this normal white blood cells. So this is the hypothesis, and we need to substitute the value in it. Once we are going to substitute the value in it, then we need to basically multiply this, or you can say we need to get a multiplication of this weight parameter with the x, and we know what we want to do. We want to predict that tumor is in dangerous condition or not. If we are talking about the dangerous condition, the probability, or you can say expectation, y is the classification, that is the positive. If we are talking in this situation, we need to determine that this should be greater than 0. So first we need to substitute the value of so after multiplication, we will get a result. Like this, theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 square plus theta 4 x2 scale and greater than 0. So if it's greater than 0, then we need to substitute the value of this. This is the, here we can notice minus 1 plus, of course, multiply this 0 whole term, this whole term 0, this whole term 0, because theta 1 is 0, theta 2 is 0, theta 3 is 1. So we will write and theta 4 is also 1, so this will becomes, so we are getting this equation. By simplifying further, this negative will go on the other side. We will get here, if we let me rewrite again, x1 square plus x2 square greater than 0. Because this one greater than 0, because we are predicting the y equal to 1, that the dangerous or malignant case of the tumor. So we need to consider this on the opposite side. So this one x1 square plus x2 square, and here it will becomes 1. So now this shows what? This shows 3 possible scenarios. First one, x1 square plus x2 square greater than 1. The other scenario is x1 square plus x2 square equal to 1, and this one x1 square plus x2 square less than 1. Very simple and beautiful concept is portraying here about the decision boundary. This one is x1, x2, and the unit, okay, 1, -1, so -1, this is 1, because we are considering, this is representing basically the equation of circle. It's very simple. Equation of circle with unit radius 1. So if we are talking about the first one, this one, inside the circle is greater than 1, this means we are talking about outer region. That is x1 plus x2 square greater than 1. So if we are getting this response, these values are greater than 1, then tumor is in malignant condition. So we will say that it's a cancer. Okay, if it's we are exactly at the border, this one, this area. So it depends where. Okay, again, if it is in the situation that clinical experts say that even it's, for example, at the middle somewhere, but you can say it's a decision boundary. At this boundary, clinical expert will decide it's in the malignant condition or not, but it's again exactly equivalent to 1, that is exactly at the boundary area. Okay, at the edge of the circle, or you can say exactly at the boundary. If it's a less than 1, this represent is benign. That tumor will be classified as a benign, that is not in a very dangerous condition. So this boundary decision help out to classify the tumor. So what we will do, once we will determine the value of this, then we need to substitute this value. Basically this value is what? This value will be utilized into the sigmoid function, and sigmoid function, this is equivalent to z, or we can say g of z, sigmoid function 1/1 plus e minus z, or we can say we will substitute 1 plus e minus this value here. So this value will be substituted here and will give us some kind of a graph. So somewhere here, if it is 0.5, and somewhere this is the 1 and this is the 0. So we are getting a curve, sigmoid function curve. So it will tell us that where it is lying. In case of x1 plus square x2 square greater than 1 here. This point x1 square plus x2 square equal to 1. This will tell us x1 less than Okay, 1. So this is the situation, though it is the, you can say unit radius is 1, but with the help of sigmoid function, we will encompass the information within the range of 0 to 1. So our output will be classified between 0 to 1. And if it is a project to 0, then it's the benign. If it is a project to 1, then it will show us some kind of a malignant concept.